Welcome everyone to Tech Excellence Conference 2024. And the next talk will be with Vlad Khononov. Vlad is a software engineer, chief architect, and consultant with extensive expertise in distributed systems and software design. He's a public speaker, a very well known one, and author of both Learning Domain Driven Design and Balancing Coupling in Software Design. He will be presenting today complexity and modularity, two sides of the same coin. Feel free to write your comments and questions in the chat below. Vlad, stage is yours.
Thank you so much, Alina. Hello, everyone. You know what? Yesterday was the Global Day of Domain-Driven Design, so I have to mention the Monkey Book, Learning Domain-Driven Design. If you have already read it, awesome. If not, you still have a chance to celebrate the next Global Day of Domain-Driven Design. But anyway, I love DDD, but today I wanted to talk about a different topic, which is also the topic of my latest book, and by the way, the last ever book, called Balancing Coupling in Software Design. And based on the title, I guess you understand that this book is about coupling. Now, I remember when I just started working on this project 5 years ago, some of my friends and colleagues were looking at me like weirdly and saying, okay, so do you really need to write 300 pages just to say that coupling is bad? Like, come on. And well, the thing is, this book is about things that we kind of understand intuitively, or rather we think we understand them intuitively, but we still have hard time defining them clearly or explaining them clearly. And when we cannot do that, we can't really use them effectively. Now, two such things that we kind of think that we understand intuitively are complexity and modularity. Now, when I'm doing this presentation offline, I usually ask the audience, hey, who here wants to design complex systems, like those scary big balls of mud? Who here wants to design modular systems? And of course, the second question gets more hands raised, but some people are also interested in design and complexity. And I'm like, okay, guys, could you please explain? And then somebody from the audience once said, well, that's job security. Anyway, if you want job security, I'll teach you how to design complexity, how to design the scariest monolith possible. But I want to also show you how to design modular systems. Now, both these topics are not easy. There are books written about complexity, books written about modularity, and I think you can easily find books about each one of them that are 700 pages long. Now, today, I have about 35 minutes left. In those 35 minutes, what I want to do is to make sure that by the end of this session, you will be able to define what is complexity, what causes complexity. You'll know what is modularity and why you should design modular systems. And most importantly, I want to give you a tool that you can use today that will allow you to steer your system towards modularity and away from complexity, or the other way around if you want job security. A tool that will help you to make design decisions that will result in a kind of system you want to design. As I said, I have about 35 minutes, no time to waste, so let's start. Both these terms, complexity and modularity, are used to describe systems. We say that a system can be complex or a system can be modular. Now, I want to start by making sure that we are on the same page about what is a system, how we define a system. And the definition that I like the most comes from Donella Meadows' classic book, Thinking in Systems. And in this book, Donella says that a system is a number of interconnected components working together to achieve something, to achieve a goal. Following this definition, you can say that systems are all around us. The computer I use here, the computer you use to watch my presentation, the clicker I'm using here, or maybe even the chair you're sitting on, all of them are systems. They're based on a number of components that have to work together. And since they're working together, we have those interactions between them. And of course, those interactions are happening to achieve a goal, the functionality of that overarching system. Now, where can we find systems in software engineering? Well, everywhere we'll look. Let's say that you're looking at a bunch of microservices working together to achieve a goal, to implement the functionality of that overarching distributed system. So we have a distributed system. Components are those microservices, interactions between them, and we have a goal, the functionality of the system. Now, let's zoom in into one of these microservices. What can we find there? Well, there we can find namespaces or packages or modules. The exact terminology depends on your technological stack, but the underlying idea is still the same. What we have here is a number of logical boundaries. Each one of those logical boundaries implements some functionality. They have to work together in order to implement the functionality of that overarching microservice. That's the goal of that system. So each microservice is a system on its own. What are we going to find if we zoom in into one of the namespaces here? Well, now we have a bunch of classes or objects. Again, they have to work together. Why are they working together? Because they have a goal, the functionality of that overarching namespace. Guess what's going to happen if we zoom into one of these classes or objects? Now we have the methods or members of that object, and again they have to work together. Again, we have those interactions. So they are working together to implement the functionality of the overarching object. That's the goal. So each class can be seen as a system on its own. And as you can see, it doesn't matter what level of abstraction we are looking at, we can find systems everywhere. Now, what makes a system a modular one? And the thing about modularity and modules is that there are lots of misconceptions about it. I will ask you, for the remaining time of this session, please forget what you might have learned about how to define a module or a component in module literature, and instead, let's see how these terms were defined way back in late 60s or early 70s when modularity was just introduced to the domain of software engineering. Back in those years, there was a methodology called structured design. It was like domain-driven design nowadays. And in that methodology, they defined what is a module. Here is a definition that comes from Glenford Meyer's book, Composite Structure Design. And in this book, Glenford says that a module is any collection of executable program statements meeting all of the following criteria, which is a fancy way of saying that a module is a piece of code that meets the following three criteria. First one is that piece of code should have a self-contained functionality. We should be able to define what is the functionality of that code, what it's supposed to do. Second, that functionality can be called from any other module. So that functionality should have a public interface so that we'll be able to execute from other parts of the system. And finally, the most important one here is that the implementation of that functionality has the potential to be independently compiled. And I highlighted that word potential here because it's super important. In modern literature, usually people say that component is physical boundary, which is compiled independently, but a module is a logical boundary, which is compiled with other modules. According to this definition, that's not the case. Whether we're looking at a physical boundary, which is compiled independently, or if we're looking at a logical boundary that can be compiled independently, we're still looking at modules. So where can we find those modules? Microservices, we have self-contained functionality of each microservice. Each one of them can expose that functionality to other parts of the system. It has a public interface, and of course, each one of them is compiled independently. That makes each microservice a module according to that definition from 70s. What about lower level of abstraction, namespaces? Again, those logical boundaries have functionality, they have public interface, and it has the potential of being independently compiled. Awesome. It can also be called a module. Objects. Again, same story. We have functionality, we have public interface, and we can compile them independently. Each class can be called a module. And we can even dig further into members and methods of an object. And again, each one of them has some functionality. It can be called from other modules, from other parts of the system. And I'm not saying that we should, but we definitely can compile those methods independently. So we can even look at methods as modules according to that definition from 70s. Now, you probably noticed that I reused exactly the same slides that I used for explaining what is a system. Again, I said that a system is a set of components with interactions between them so that they will be able to achieve a goal. Now, does it mean that a module is simply a synonym to the word component I used before? Well, not exactly. If we're looking at any system, and by that I mean any system, even my chair here, we have a number of components, interactions between them, and the goal it has to implement. Any software system that you are implementing meets that definition. If it works, it achieves its goal. It implements its current functional requirements. However, modular design expands the definition of the system's goal to accommodate requirements that might be needed in the future. By that, I don't mean that it has to implement each and every idea that might come up to domain experts' heads in the future, each and everything that they might ask us to implement in the future. No. The idea is modular design should make it easy to implement those reasonable changes that might be required in the future. Again, reasonable changes. If you have a CRM system and tomorrow you want to turn it into a driver for a printer, that's not a reasonable change, okay? That's not what we are talking about here. What we are talking about here is if we have a CRM system and tomorrow we want to integrate it with a notification sending system, then it should be easy to implement. That's the goal of modular design, to make those future changes as easy as possible. So to sum it up, the goal of modularity is to design a system in such a way that will have a number of components, interactions between them, and it will support not only the implementation of its current goals, but it will also accommodate the implementation of future goals. Now, we cannot take any system just divided into some set of boundaries, let's call them components or modules, and hope that it will result in modularity. That's not going to happen. In 99.9999% of cases, that arbitrary decomposition won't result in modularity, but it will result in complexity. So let's talk about what is complexity, because unless you want job security, modularity is what you want to achieve. Complexity is what you want to avoid. So what is it? Jeffrey West, the author of the book Scale, defines complexity as something that you know it when you see it. That's an amazing definition. It's correct. When you see complexity, you have that feeling, oh, hey, okay, we're dealing with complexity here. However, in order to manage complexity, we need a more precise definition that we can work with. And the definition that I like the most comes from the Khononov framework. Khononov framework is a tool for making decisions in different types of situations. Because let's say that you have to make design decisions in two different kinds of systems. They're designed differently. One is designed as a complex one, as a big ball of mud. The second one is defined as a modular system. Well, there are different decision workflows you have to apply in each one of these cases. That's the overarching goal of the Khononov framework, to provide you with the exact steps you have to take to make decisions in different situations. For example, let's say that you are working on a system and you want to make a change, and you know exactly what the outcome of that change is going to be. You make the change, you're looking at the system's behavior, and the change in its behavior is exactly the same one as you anticipated when you made that initial change. In that case, we are not dealing with complexity here. That system is clear or obvious. What if, on the other hand, let's say that you want to make a change and you have no idea what the outcome of that action is going to be. However, you can consult some external expert, maybe your colleague or some consultant that you can call, say, hey, that's the system, that's what I want to do, what's going to happen, and that external expert will tell you exactly what's going to happen. Again, that's not complexity. What you're dealing with here is called a complicated domain. That's the language of the Khononov framework. You are dealing with a complicated system, not a complex one. Now, what if you want to make a change, you have no idea what's going to happen, and the only way to find out what's going to happen is to make the change and then just observe the outcome. See what's going to happen. That's, in the language of complexity, in the language of the Khononov framework, is complexity. A system that is designed in such a way that if you want to make a change, the outcome of that change or of that action you want to take can only be identified in retrospect. You have to conduct an experiment and observe its results. That's the definition of complexity according to the Khononov framework. Where can we encounter such complexity in software design? Well, we have quite a few opportunities, right? I guess everyone here had the pleasure of working on a big wall of mud code base where you are changing a line of code and you have no idea what's going to happen, or maybe you think you know what's going to happen, but then you deploy it to production and then you have a few surprises. For example, some unrelated parts of that system stop functioning properly. Well, that's complexity. You could only find that out in retrospect. On the other hand, maybe you get a set of new business requirements that you have to implement, but you don't know what parts of the system have to be modified to accommodate those new requirements. Maybe it looks like you get a new set of business rules and okay, you find a module where those rules are implemented, you modify them, awesome. Deploy it to production, and a week later, Suddenly, that system is not in an incorrect state, and you start investigating what happened there, and you find out that the same rule is implemented in multiple places and you didn't update one of them. Again, that's complexity. Now, where can we observe that complexity? On what level of abstraction? Microservices? Easily. If we make a change and suddenly some unrelated microservice stops functioning, well, of course, we can find the complexity on this level of abstraction of distributed systems. If we zoom in, again, the same slides, of course, it can happen here as well, between namespaces and between objects and between methods of the same object. We can observe those complex interactions on all levels of abstraction. Let's use the following two terms. Local complexity, I will use it to denote complexity of the component you are working on. Let's say that you're modifying an object and you have no idea what the outcome of that change is going to be in the behavior of that specific object. So we'll say that it has high local complexity. If, on the other hand, you know what's going to happen in that object, but you don't know how its interactions with other objects of the system are going to be affected, then we'll say that it's global complexity. That we have complexity in the overarching system of the module that we are working on. So that's complexity. Of course, it is driven by the design of a system, right? You can design a system as a modular one or as a big ball of mud. So one will result in complexity, the second one won't. But what really causes that complexity? Is it only about the design of the system? Well, not really. Actually, complexity is primarily caused by us or by our cognitive abilities. Once the complexity of that system reaches the threshold of our cognitive abilities, once we can no longer anticipate results of changes, we are going to say that that system is a complex one. Maybe 10 years from now, LLMs will be so advanced that they will be able to take any big ball of mud that you put there and they will generate what exactly is going to happen if you change something. Well, suddenly we'll have much less complexity around us. However, in the meantime, in 50s, they did an experiment to try to measure that threshold of our cognitive abilities and came to realization that we can hold 7 plus minus 2 units of information in our heads simultaneously. The same experiment was repeated 50 years later. Now the result was 4 plus minus 1 units of information. So as you can see, the trend is not positive. We are not doing good, right? We need those LLMs to help us to address complexity. So I said that the goal of modularity is to design a system in such a way that it will help us to implement those future changes, those future goals. Combined with the definition of complexity, we can say that the goal of modularity is to minimize the cognitive load that is needed to evolve the system in the future. We want to optimize that cognitive load that the person working with the system will face in the future. That person, by the way, maybe it could be you, it could be your colleague, whatever. How do we do it? How can we identify what design decisions are going to result in increased complexity and what design decisions are going to result in increased complexity or in increased cognitive load? Well, it has something to do with coupling. Let's see. Let's say we have two components. Doesn't matter what those components are, on what level of abstraction they are located. They can be methods, they can be microservices, doesn't matter. What's important for us here is that we have that yellow line, that pipe between them that connects them. It means that these two components are integrated. They're working together. Through that pipe, we can observe data. That data will flow from one component to another one. For example, component A can say, hey, component B, give me some information. Well, component B says, okay, here's that information, here's that data, take it. Or it can issue a command, an instruction to do something, so it will send data about what it has to execute. And data, of course, is important, right? We need to exchange information between parts of the system in order to achieve its goals. However, when we are talking about modularity and complexity, that's not the most important part here. There is another thing, another kind of energy that flows across any two coupled components. It happens across all levels of abstraction. There is something else that these components have to exchange in order to be able to work together, in order to be able to integrate with each other. And again, going back to the definition of a system is not just a number of components, but interactions between them. So in order for those interactions to happen, we need that something else. And I'm playing for time here because I want you to think what that is. That's not data. What else? What else needs to be exchanged between any two coupled components in any system in order for them to be able to work together? Usually, when I'm asking this question in offline conferences, I hear answers such as public interfaces, which is correct. In order to call a functionality that is implemented by another component, I need to know how to work with its interface, how to integrate with it. Someone else will usually say business logic. Well, of course, if I want to integrate with another component, I need to know what is the service, what is the functionality provided by that component. I need to know its functionality. But I prefer a more abstract term, and that's knowledge. In order to work together, any two coupled components have to exchange knowledge. That knowledge can come in different forms. What's important for us here is that the more knowledge that is shared across any two coupled components, the more they will have to change together. The idea is the more knowledge we are sharing, the higher the likelihood that some piece of that knowledge will change and will cause cascading changes across that pipe that connects the two components. Now, how do we quantify knowledge? What are the units that we can use to evaluate that amount of knowledge? That's hard. And I don't think that it's possible, at least today, to quantify knowledge. So instead, what I want to propose is, instead of quantifying knowledge, to differentiate across four fundamental types of knowledge. Four fundamental types of knowledge that can be shared across any two coupled components. Again, any level of abstraction, whether we're talking about high-level distributed system, or maybe even across systems, or even methods within an object. Whatever the level of abstraction is, we can observe four fundamental types of knowledge. That's the model that I called integration strength. It has four basic levels: integration coupling, intrusive coupling, functional coupling, model, and contract coupling. Let's go over them, and I will start with the highest one, intrusive coupling. The idea here is that each type shares considerably higher amount of knowledge than the previous ones. So if we can identify those types, we don't really need to evaluate to weigh that knowledge and to find those magical units for quantifying knowledge. We just need to categorize the type. So the first one is intrusive coupling, and this one shares the highest amount of knowledge possible. Let's say that you're implementing a microservice. Now, a microservice has a public interface, and we all know that you shouldn't access another microservices database directly, but you should only interact with it through its public interface. Now, here I am, and I say, okay, that's fine, but give me a database. I'll just connect to your database, take whatever information I need, maybe even modify something because, hey, why not? If I'm already there, I'll make some changes because maybe I don't like your public interface or maybe I'm just too lazy. For any reason, what I'm doing here is I'm introducing intrusive coupling. I'm introducing a dependency on your private interface, on the implementation details of your service. The implication of that is that the integration method I am introducing is fragile and implicit. You might not even be aware that I am doing that stupid stuff, right? Any change to the implementation details that you might make in the future in your microservice might cause the integration to stop working. It would be totally unexpected for you and most likely to me as well. That's why with this level of integration strength, intrusive coupling, we have to assume that all knowledge is shared. All knowledge about how that upstream component is implemented is shared with other components that are integrating with it. Now, this level is about how a component is implemented. Whenever that how changes, it can trigger cascading failures and changes in other components. The next level, functional coupling, is more about what is implemented by the components. So we'll say that two components are functionally coupled if they're implementing closely related business functionalities. The practical implication is that the same changes in the business requirements are going to trigger simultaneous changes in both our components. If you're familiar with domain-driven design's terminology, then probably our two components belong to the same subdomain, so they will be affected by the same changes in the business requirements. Now, the extreme example of functional coupling would be two modules that are implementing exactly the same business logic or exactly the same business rule. They might not even be integrated with each other. All they're doing is just implementing, duplicating the same business logic or the same business rule. And if their implementation will go out of sync, then the system will end up in an incorrect state. In that case, we have an extreme case of functional coupling. Whenever one changes, the second one has to change as well. So again, we have a quite high amount of knowledge that is being shared across those two components because the likelihood of a change in the business requirements to trigger a cascading change across two components is quite high here. So that's the second level of integration strength, functional coupling. The third one is model coupling. And our job as software engineers is hard because we have to work on different business domains. Today, you might be working on a financial system, tomorrow on a medical system. You cannot expect yourself to become a domain expert in each one of these fields, right? You cannot learn in each and every type of knowledge or information about those financial or medical domains or any other types of domains that you might work on. So instead, when we're implementing software, what we're doing is we're building a model. We are taking only the parts of that business domain that are relevant to the problem that our system is supposed to solve. So we are building a model of the business domain. Again, I'm wearing my DDD hat. If you're into domain-driven design, you probably already know the importance of crafting effective models, and how important it is to evolve those models if suddenly you have new insights or new knowledge about that business domain. Now, let's say that we have two components that are based on the same model of the business domain. That means in order to change that model, we have to modify two of the components. So again, we have that knowledge of model of the business domain shared across two components, and whenever it changes, we have to change them simultaneously. Is it good or bad? We'll talk about it in a few minutes, but again, the implication is that it can hinder the evolution of that model. And finally, the lowest level of integration strength is contract coupling. And here we have components that are integrated through an explicit integration-specific model. Think about it as integration-specific model of the implementation model, a model of a model. And the goal of that integration-specific model, that integration contract, is to completely encapsulate all implementation details of a component. All the information about its implementation details are encapsulated, all information about its function requirements are encapsulated, and all information about the models it uses internally is encapsulated as well. So we can change the model, and in most cases, the integration contract will stay the same. It will be more stable. The goal is to come up with an integration contract that will be much more stable than the implementation model. The DD hat, open host service, published language, anti-corruption layer, all these patterns help you to define that integration contract for bounded contexts. So this is the integration strength model for fundamentals, for fundamental types of knowledge. Whenever we are going higher on the scale, we have higher integration strength and we're sharing more knowledge. As a result, also, we can say that the higher we are on a scale, the more implicit our integration interfaces are. Again, the highest extreme is intrusive coupling. You are introducing integration that the other part of the system might not even be aware of. So it's very implicit. Whereas contract coupling is the most explicit one because you have that integration contract. Now, sharing knowledge is, of course, important, but that's not the whole picture. Let's look at another dimension, a spatial dimension that I call distance, the physical distance between any two coupled components. And by that I mean, is their level of abstraction, because we can observe coupling between statements of a method, between methods, classes, namespaces, components, services, and even whole systems. The higher we go on this scale of distance, the higher the physical distance between the source code of those components. Again, if we are modifying the same object, maybe we have to modify two methods within the same object, then they will probably be in the same file, so they're close to each other. Whereas if we have to modify two microservices, then probably, most likely, they will be in different repositories and they will have different life cycles. So much higher distance between them. Why is that important? And again, that's a question that I usually ask when I'm doing this talk live. And again, I'm playing for time because I want you to think what is represented by that vertical axis here. Why is that important? Well, that's important because the higher we go on the scale, the higher the coordination effort we have to invest in order to implement a change that affects both coupled components. Changing two coupled objects or two coupled methods will require significantly lower effort than two coupled services or two coupled systems. So we can say that the cost of a change that affects two coupled components is proportional to the distance between them. The higher the distance, the higher the cost. And now, when we have those two dimensions, integration strength and distance, let's look at extreme combinations of these forces. Let's say that we're looking at two components and we can observe low integration strength between them, which means they're not sharing much knowledge, they're minimizing the knowledge that is shared between them. And the distance between them is high, which means that the cost of changing them simultaneously is going to be high. However, since we're minimizing that knowledge, we're also minimizing the probability of cascading changes. So we are okay here with this relationship. That's what we usually call loose coupling. We have high distance between components, high effort needed to evolve them, but our design minimizes the probability of such cascading changes. What about the opposite? Let's say we have high integration strength, which means those components share a lot of knowledge. And that doesn't necessarily mean the design is bad. Sometimes you do have to share lots of knowledge. Sometimes you do have to implement components that implement a related business functionality. So you have functional coupling. Sometimes you need to base your components on the same model of the business domain. So you will have model coupling. There's nothing you can do here. So let's say we're in that case. We have high integration strength, which means they're very likely to change together. However, these two components are located with low distance between them, which means the cost of making cascading changes is going to be low. That's why we call this relationship high cohesion. Again, that's a good one. Yes, they will co-evolve, but our design makes it easier to co-evolve them. They are located close to each other, so we are optimizing the cost. We're taking the cost of changing them down. Now, what about this one? Low integration strength. We are not sharing much knowledge, but also low distance between them. And each one in isolation sounds good, right? We are not sharing much knowledge. They are not going to change together. That's okay. We have low distance, so we're minimizing the cost of making cascading changes. That's also sounds good. However, the combination of the two is not really good. It's not good because what you are doing here is you're placing unrelated things close to each other. Whoever will evolve that overarching module or component in the future will have to make their way through those unrelated parts of that component to find the thing that they have to change. In other words, this relationship increases the cognitive load on the person that will have to change that component. So we'll say that this relationship is local complexity of that single component. Now, what about high integration strength over high distance? So we have two components that will change together because of high amount of knowledge that they're sharing, and we have high distance between them to make our lives even more miserable, which means not only will they change together, but it will also require lots of efforts to implement those changes. Well, that's global complexity. Again, local complexity is complexity of component, a single component. Global complexity is complexity of the overarching system. So overall, we have 4 different kinds of relationships. If you want job security, you have red squares. If you want a modular system, you have green squares. Overall, if you want modularity, then integration strength and distance have to be inversely proportional to another. So, in binary scale, we can say that modularity is integration strength XOR distance. Or to minimize it a bit more and a bit more, M, S, XOR D. Or somebody said, that reads like me said. So you can use it to remember this relationship. How can you apply this in your day-to-day work? Well, first, always minimize the integration strength. Minimize it as much as possible. But again, remember that it's not always possible to be on the lowest level, on the contract coupling. Sometimes you do need to use the same model, sometimes you need to implement related business functionalities, and sometimes you need to uh, integrate through implementation details. So refactor your system to the lowest possible level of integration strength. Once you've done that, balance the distance. If both are high, then you have to reduce the distance. If both integration strength and distance are low, then you can increase the distance. Again, with both of these changes, you're optimizing the cognitive load, or in other words, you're reducing complexity of the system and you're making it more modular. I am out of time, so to wrap it up, again, a system is a set of components with interactions between them in order to achieve a goal. Modularity or modular design expands the goal of a system to the future. I used complexity to define I used Cynefin framework to define what is complexity in the terms of how predictable is the outcome of an action you want to make. And we analyzed different combinations of integration strength, of shared knowledge, and distances between coupled components. With those two dimensions, we can say that modularity requires integration strength to be inversely proportional to distance. That's it. I'll just say that you can use this tool right away, but if you read the book Balancing Coupling and Software Design, you will find a more intricate ways of evaluating integration strength. You will learn about different degrees that those levels have so that you can compare to integrations of the same type. You will also learn about an additional dimension of coupling, which is volatility, which can also cause some expected and unexpected changes in your components. And with that, Lena, back to you. Let's see if we have questions.
Thank you, Vlad, very much. I guess we all want job security, but please let's stay in green squares. We do have a lot of comments and questions. And first of all, we got a recommendation from Lemi. I highly recommend Vlad's book. I read it all, but it's one of the cleanest book in that subject. So thanks, Vlad, again for your amazing books.
Thank you, Lemmy. Thank you so much.
Okay, let's check this one. How would you measure the coupling in an automated way? Do you use a tool for that?
No. Look, there are tools to measure coupling in automated ways. You have static code analysis tools that will count variables that are being accessed from different parts of the system. Those tools will produce you a number, but that number is problematic because it doesn't take into account what that variable means. That variable can be a part of an integration contract, or it can be a part of implementation detail, for example. Now, let's say that you have hundreds of fields from integration contract versus one field that is in implementation detail. Well, the numbers are different, but the intentions are way more different. So right now, the static code analysis tools that we have, they don't know the intent of that knowledge that you're sharing. That's why at this moment, I prefer to rely on a meatbag person to read the code and understand what's going on there. Now, I tried to implement such a system. I gave up. In the book, in a related chapter, we'll find a footnote saying that, hey, if you want to take the challenge, you're more than welcome. I would love if somebody succeeds to implement such a system that will measure the coupling in an automated way.
So if there is a system already developed, one, you can contact Vlad and
Yeah.
share this knowledge with you.
Yeah, let's work together.
Good. Let's move to the next question. I guess you're the right person for this one. How to define module boundaries in a complex domain?
So again, let's say that you have that complex domain. And by complex, what you mean here is, if I understand the question correctly, is complexity of the business domain, not of your solution. This talk was about complexity of your solution, not of the problem. When you have a complex business domain that you have to work with, you need a tool to understand what's going on there. It's more related to domain-driven design. The first domain-driven design book is called Tackling Complexity in the Heart of Software. So DDD provides a set of tools and practices for learning the business domain and for managing its complexity, like bounded contexts that encapsulate different models. Each model is implemented to each model is designed to address a specific problem, etc. That's the part of the problem domain. Now, the solution domain should manage that complexity as well, and this was the topic of this presentation. Again, knowledge sharing. Optimize how knowledge flows across the system. If you divide your system into modules in such a way that they exchange lots of knowledge, then probably that's not going to be good for your modularity. If you optimize that knowledge, if you divide it into components in such a way that minimizes the knowledge that is shared between them, then you will lower the cognitive load and you will make it more modular. So to sum it up, two parts: problem domain, you have domain-driven design to deal with the complexity of the problem domain, to understand the problem, and these tools to design modular systems.
Thank you very much. We still do have 4 more minutes. Let's try to answer 1 to 2 more questions. How can we convince a team with tight deadlines and a complex system to invest in modularity to improve long-term reliability and speed?
Hey, Felipe. Well, if you have tight deadlines, then you don't have to to convince the team. You have to convince the management to do something about it. You have to explain to them that, okay, if we don't do something about the design, then our ability to meet your future business goals is going to be significantly reduced. So I would say that don't try to convince the team, talk with the management, and explain in business language the implications of the current situation.
Thank you very much. Let's go to this question. What about apparent coupling and efferent coupling?
Yeah, whoever invented those terms, that person hates ESL speakers, like efferent. How do you differentiate between the two? So now seriously, in the book, in these slides, when I showed you two components with that pipe between them, there was no direction there. Of course, the direction of the knowledge flow is important. In the book, I use the terminology of upstream component and downstream component. Upstream is the one that shares knowledge or the functionality provider. Downstream is the one that receives that knowledge in order to integrate with the upstream. So knowledge flows from upstream to downstream. The implication is if the upstream shares lots of knowledge, the downstream is going to suffer, probably in some cases. So that's my take on it. It's a part of the model that is described in the book, but I prefer terminology that is more kind of domain-driven design style, upstream, downstream, than afferent and efferent coupling.
Thank you. And let's pick the very last question. Is integration strength versus distance related to the principle known as the law of Demeter in OOP? What's your opinion about it?
Yeah, absolutely. But the interesting thing is, if you look at design patterns and design principles in general, and you analyze them in terms of integration strength and distance, and some of them in terms of volatility as well, that's the third dimension from the book, you will see that all of them share those relationships underneath. They're just providing different names, but the underlying concepts, the underlying principles are the same. And that's the last chapter of the book. It shows how the coupling formula can be observed in design patterns and architectural patterns, in design principles, etc. So yeah, absolutely great observation.
Thank you very much, Vlad, for being with us. And we are moving to our next session. Susan Kaiser will present in the next session optimizing for a fast flow of value with architecture for flow. We already have recordings if you missed previous sessions, and you can join other live sessions today, whole day. Very big thank to our sponsors. If you want to learn more about software craftsmanship products, please check these online courses and join us on Meetup and follow us on social media. See you in the next session.